everybody. This is Christiane Bixel. I'm with Palo Biotech, and we are presenting to do a new episode of Palo Academy. And we go right into it. Good morning, Tommaso. Just go ahead.
Good morning. Good morning. Hello, I'm Tommaso Sbrana, and I'm the CEO of IVTech. In the last 13 years, I focused my attention in the development of new tools to overcome the limitation of a multiple plate or transport system in order to refine and increase the predictivity of the in vitro models if compared to the human reality. In 2014, I founded IVTech in order to bring this solution onto the market. So in this presentation, I will focus the attention on the receipt that we would like to promote in IVTech in order to develop advanced in vitro models. You will see a first part of the presentation focused on scientific data, in particular showing the study about the glaucoma, and then I will shift my attention onto the IVTech and the technology that we promote. So in IVTech, we think that we need to increase the complexity of the standard in vitro model in order to increase the predictivity of the human reality. So we are talking about 5D in vitro model. The first three degree of complexity are related with the configuration, the 3D configuration of the 3D model. Then we had also a fourth dimension related with the dynamicity of the environment. So basically we have the opportunity to have medium in flow condition, which recreates the blood action in human circulation. This is not enough because, as we know, the response to an exogenous stimulus is a modulation of different organs. So we have also to consider this aspect in our in vitro model. So the fifth dimension of our 5D in vitro models is represented by the cross-modulation between different tissues. In case of the need to recreate a disease, a human disease, we can structure this problem on different levels, and we can optimize each level in order to obtain a complex in vitro model. So the different levels are represented by the biology issue, so the 3D configuration of the tissue, as well as the cell phenotype that we have to choose in order to replicate the functionality of that particular tissue. Then we have to consider the environment, so the dynamicity of the environment. Each tissue requires a certain flow rate, a certain dynamic condition in order to replicate their functionality. But we have also to consider that, in particular in the disease model, we have also to have stimulation pathways, such as an increase of pressure, for instance, in the glaucoma or in the hypertension. So we have to consider also this aspect in our advanced in vitro model. Then we have to evaluate the crosstalk between different tissues. This is crucial once you have to mimic a disease, because in particular in this kind of in this scenario we have an evolution of the disease that starts onto a certain tissue and then affect different tissues. So we need to recreate this cross-modulation, and from the drug point of view, this means that we can test the principal effect of the drug, but also the side effect onto the related tissues, as well as evaluate its bioavailability in our pathway. So in this presentation, I would like to give you an idea of this complex scenario, showing how it can be used in the study of glaucoma. So as I told you, the first part will be focused on scientific data that has been provided by a research group in Genova, Italy, directed by Professor Bassi. And then I will shift the attention onto the technology. So glaucoma is the second cause of blindness worldwide. It can be classified as primary glaucoma or secondary glaucoma. The most common disease is the primary open-angle glaucoma, affecting up to 52 million adults in 2020. The risk factors are related with age, gender, family anamnesis, and also ethnicity. In standard condition, in our eye, we have a continuous exchange of liquid between the anterior and the posterior chamber. in case of glaucoma, this scenario is not anymore valid because we have a tissue damage and we have a failure in the liquid exchange. The liquid that is not drained anymore in the anterior chamber increase the pressure in the posterior chamber. And this increase of pressure is the cause of optic nerve damages and in particular of blindness. The key event is related with trabecular meshwork, which is a spongy tissue between the anterior and the posterior chamber of the eye. So as you can see, the glaucoma is a very complex scenario where we have different stimuli that we have to consider, and we have also an evolution of the pathology. So at the beginning, we are talking about trabecular meshwork, then it affects different tissues such as the optic nerve. So this complexity is hard to be simulated using a standard in vitro model. So we need something more in order to consider all the stimuli as well as the crosstalk between the tissues. So that is the reason why in Genova they decided to use our technology in order to solve this problem. So we will see more details in the second part of the presentation. However, the IVTech platform can be characterized by a cell culture chamber, in this case called Livebox 1, which is a bioreactor where we can see the cells in 2D or in 3D configuration, exposing to a dynamic environment. In this dynamic environment, we have the flow of medium due to the action of a pump called live flow. This is a peristaltic pump that is used to let the medium flow in a fluidic circuit and perfuse the Livebox 1. Then we have a module called Live PA, which is a pressure modulator. This module can be used in order to increase the pressure onto a specific tissue, and as we will see, it has been used to replicate the increase of pressure, so the IOP, which characterized the glaucoma. Of course, we have also the cell culture. The first step is to establish a 3D model and decide which kind of cells that we are going to use in order to replicate our tissue. So in Genova, they evaluated, they decided to use human trabecular meshwork cells, and they, as a preliminary data, they evaluated the differences between a 2D and a 3D model in static condition. I'm not talking about this data, but if you're interested in having more information, you have the reference to the paper in the bottom part of this slide. So my talk starts once we have the 3D model in static condition already standardized. So once we have this configuration, we need to start the dynamic stimulation. So researchers join the fluidic chamber to the pump and starts the flow of medium. So the experiment took take up to 7 days, and they expose the cells to an oxidative stress represented by hydrogen peroxide as a certain concentration. So at the end of this stress analysis, they evaluated different endpoints in order to evaluate the effect onto the 3D tissue comparing with the untreated 3D tissue. So the first results are related with the morphology of the cells. So they performed the confocal analysis, and here we have the reconstructed pictures. So in dynamic condition, we observe thicker nuclei as well as actin filaments. At 72 hours, we have a reduction of actin filaments intensity, both in static and in dynamic condition in the treated models if compared to the control. At the end of the experiment, so after 7 days, in a static condition, we have an increase of of intensity reduction, and this is not observed in dynamic condition. In dynamic condition, we observe a recovery of the actin filament intensity, and this could be related with an adaptive phase that cells encounter in the dynamic environment. So we have to think about a funnel. At the end of this funnel, we will have a tissue which is ready to work in dynamic condition. And this is a theory, but it will be confirmed by the data that I'm going to show you. From the apoptotic point of view, we can analyze the protein level of the pro-apoptotic protein level. As you can see, in a short-term analysis, we can have an increase of pro-apoptotic protein levels, both in static as well as in dynamic condition. But at the end of the experiment, we have a balancing of anti-apoptotic protein levels in dynamic conditions. So the pro-apoptotic and the anti-apoptotic protein levels are balanced in dynamic condition, and this is not observed in static condition. Again, this is a proof of this adaptive phase of the tissue in dynamic condition. Moreover, we can also evaluate different biomarkers, such as the PARP cleavage that is observed in static condition and not in dynamic condition. And from an inflammatory point of view, we can also evaluate the level of the NF-κB-P75 protein, and this the increase of the level of this protein in dynamic condition seems to be related with the triggering of inflammatory cascade. So again, we have an adaptive phase in dynamic condition that is not observed in a static condition. So once the tissue has been characterized with this preliminary data, the researchers decided to use this platform in order to test the effect of a drug, and in particular, iTrub. iTrub is a mixture of polyphenols with antioxidative properties. The reason why they choose this kind of drug is related with the fact that the standard therapy of glaucoma is focused on the treatment of the IOP. So the question is which is the meaning of the ROS production, so which is the contribute of the oxidative stress in the damages of the tissue. So as we will see, also the oxidative stress has a crucial role in the stress, in the damages of the tissue. So the use of iTrub could represent a new therapy, or let's say a way to have a more efficacy, a more efficient therapy of glaucoma. So starting from the standard platform that I described you before, researchers decided to expose the oxidative stressed cells to the iTrub in order to evaluate the effect. And then at the end of this evaluation, they have a cells recovery for 20 hours. Let's see the results. The tissue that is exposed to iTrub show a reduction in ROS production by 3 times if compared to the tissue that is only stressed with oxygen peroxide. Moreover, in an iTrub case, we have also an increase of cells viability after 72 hours. From the apoptotic point of view, we can expect an increase of a pro-apoptotic protein level in case of tissue treated only with oxygen peroxide. And in case of iTrub exposure, we have an increase of the anti-apoptotic proteins that is related with the iTrub antioxidant properties. Moreover, it seems that also ITRAB has also properties of anti-inflammatory properties. So we have a modulation of the level of NF-κB P65 if compared to the untreated tissue. So again, ITRAB could represent a way to increase the efficacy of the therapy, but of course it will be required more data. At this point, researchers decided to increase the complexity of the in vitro model. So again, we are in the modular approach, so they can increase the complexity of the model, adding a new environmental stimulation. In this case, they decided to implement the increase of pressure. Using our live PA, it is possible to increase the pressure on a particular tissue. And they obtain 4 different case of studies. The control case, the oxidative stress cells, the cells exposed to the increase of pressure, and then also the complex model represented by the oxidative stress cells plus the increase of pressure. At the end of this stimulation, they recollect all the medium in order to condition a neuron-like cells model, which represent the optic nerve. And this model has been developed starting from neuroblastoma cells, they differentiated using retinoic acid. Both the human trabecular meshwork as well as the neuron-like cell seems to be less sensitive to the increase of IOP if compared to the oxidative stress cells and the pathway oxidative stress plus increase of pressure. Moreover, we can observe also a modulation, an evolution, of the disease. So as you can see, after 48 hours, we have a certain level of cell death in human trabecular meshwork, which is related with, in particular, with the group where we have the oxidative stress and oxidative stress plus increase of pressure. And after 72 hours, we have a modulation of the apoptotic phase. And this is observed also in case of the neuron-like model, but we have a delay. So in this case, we observe an evolution of our disease as it is expected from the in vivo observation. So again, it is crucial to have a cross-modulation between different tissues in order to replicate in our in vitro model the human disease. So in conclusion, the modular receipt to develop an advanced in vitro model of a human disease can be applied to different pathology. I show you an example related with glaucoma. Lightbox 1 allows to develop a 3D model of different tissues in a proliferative condition, and it is also possible to expose cells to different stimuli in order to recreate, in a step-by-step modality, a complex in vitro model. And in our simulation, the crosstalk between the tissues has a crucial role once we have to evaluate the effect of a drug or even to study a human disease. So I hope that I get your attention in order to introduce you IVTech and the technology that we promote. So IVTech has been founded in 2014 as a spin-off of the University of Pisa. We are not anymore a spin-off, but over the years we have released several products on the market, increasing our products portfolio. In 2020, we have up to 6 chambers on the market. In 2021, 7 chambers, 3 pumps, and we sign agreement with different distributors in Europe and outside European borders. Our core values is to be innovative, increasing the predictivity of human reality, but maintaining a sustainable approach also from an economical point of view. Our business model is structured on three main pillars. The first one is to provide technology through a distributor network. Then we want to help our customer offering engineering services for instance, in the fluid dynamic computational analysis, as well as mathematical model to scale down the dimension from the reality to the in vitro model. We can also offer the opportunity to develop the biological aspect of the in vitro model in collaboration with certain partners. Our mission is to fill the lack between a 3D and static model and a 5D in vitro model. So we want to add a fourth dimension related with the dynamicity of the model, and then a fifth dimension related with the crosstalk between different tissues. How we can do that? Using our platform. So our platform is composed by cell culture chambers, tools to control the dynamic environment, and tools to control the environmental stimulation pathway. The application scenario is very wide, so we have studies in the metabolism as well as the test of new material, and as I introduced you in the first part of the presentation, we have also the development of a disease model. In detail, we offer two different lines of cell culture chambers. Lightbox 1 is a single flow bioreactor developed for attached cell culture condition in proliferative 2D or in 3D configuration. And it is compatible with the cell growth area of 6, 12, and 24 well plate. Lightbox 2 mimics the transwell, and it's a double flow bioreactor. It's equipped with a removable and porous membrane, and it's developed to study physiological or pathological barriers in dynamic configuration. In this case, we have compatibility with the cell growth area of 6, 12, and 24 transwell system. Live flow is the name of our peristaltic pump. It's a very small, compact, and low-weight pump compatible with the incubator environment. It's equipped with 2 independent motors in order to develop 4 experiments in parallel or 2 different experiments characterized by 2 different flow rates. It's available in 2 different versions, the standard one and the programmable version. We can use the standard cell culture protocols using our chambers because of the compatibility in the cell growth area between Lightbox 1 and the well of a multi-well plate system, and Lightbox 2 and the transwell system. The procedure that we have to follow in order to see the cells in our chambers is very similar to the standard one. So we have to open a sterile chamber, we have to see the cell suspension. In case of floating scaffold, we can fix in position using a plastic disc. We close the chamber and we clamp the system. So tissue will mature in the incubator environment, and once it will be ready, we will join the chamber to the fluidic circuit and the peristaltic pump in order to start the dynamic stimulation. It is also possible to acquire images in real time because of the transparency of our chamber. As you can see, we have compatibility with a standard inverted microscope stative, but also advanced optical imaging platform. It is possible to have a multi-organ approach, mimicking different tissues, focusing the use of different modules to mimic different tissues. We can join together different modules in order to have an exchange of liquid between these tissues and having the crosstalk in this pathway. This is crucial once we have to test the effect of a drug in order to evaluate the principal effect and the side effect in only one experiment. the final system is a very compact product, compatible also with the smallest incubator on the market. Then we have our tools to control the environmental condition. I already introduced you LivePA, which is our pressure modulator. So using this product, it is possible to increase the pressure on our tissue in order to replicate a disease condition such as hypertension, glaucoma, the presence of a mass such as in a glioblastoma scenario, but it can be used also to characterize different tissues in our pathway. For instance, in case if we are studying the GI duct, we would be interested in having different pressure along our model. Last but not least, this is the result of our research. It's still an ongoing project, but I would like to introduce you our system, our concept to acquire tear in real time. So tear is a very well-known parameter to characterize the confluency of barriers. So it is possible to acquire in real time this measure using our technology, avoiding the need to stop the experiment, dismount the system, and interact with the tissue. So in conclusion, IVTech products allows the use of standard cell culture as well as monitoring protocols. It is possible to recollect all the biological material at the end of the experiment because the support, such as the glass disc as well as the membrane, are removable. So we can recollect all the attached biological material and perform a post-processing in a plate or in a Petri dish. The whole system is compatible with the incubator environment. It is possible to develop a multi-organ approach, and also it is possible to recreate the environmental condition and evaluate the cell's behavior in real time using our system. So thank you for your attention. Here we have my direct contact, and if you're interested in having more information, please follow us on LinkedIn and on our YouTube channel. Thank you again for your attention.
Yeah, thank you, Tommaso, for the great presentation. I know you already also have a white paper published on those data. So if anybody's interested, just let us know, yeah, to get some more details and some more infos. And I think Tommaso will also be very happy to share the presentation with you again.
Yes,
if you need it on paper, or just send us an email. Thank you, Tommaso. This is very helpful. Yeah, hey. Yeah, now it's time to ask you questions. I think this was very comprehensive, and thank you also for the sum up at the end. I think it's always good to know what we can use it for. And as I already mentioned, I like this multi-organ testing, so you really can save time and money, and it's pretty easy. And Tommaso, I also know you did some workshops in the last couple of years. Do you do this also this year?
We will start again this year with our workshops. Because of COVID, we had to stop our training action, but we will start again, and probably in May or in June we will have our first workshop this year.
Yeah, exciting. Yeah, we all are waiting for May. Everything gets warmer and
Yes.
with less viruses, hopefully.
We need it.
So, yeah, it's gonna be. It's coming. It's coming for sure. Or things are different, just different. Okay, so thank you, everybody. And it's now a good time to ask questions. Tommaso will answer them live. I can also unmute you if you like to do so. I think one good question would be, how long does it take to set up the thing with the chambers? We saw a movie now, so this looked pretty easy. Yeah.
Well, the usability of the chamber has a very low barrier level. So we can use the standard procedure in order to be as fast as possible, to be ready as fast as possible with our experiment. In general, the training phase in the use of our systems took up to 1 day. So after this period, the researcher in general is able to perform an experiment in dynamic condition. Of course, as I told you, it's a matter of model complexity. The complexity has increased over the time.
Yeah, but the experiment itself, it just takes how long? An hour? What would you say?
It's a very short period, a few hours, and you can start with your own experiment.
Yeah, and you have your results you can really rely on. Yeah.
Yeah.
So, Tommaso, what else do you have in the pipeline at the moment?
I'm sorry?
What else do you have in the pipeline already? We heard now about.
We are focused on environmental control tools. So as I show you, tier platform will be our next release. We are almost ready, and it's under test in a biological partners lab. And then we will focus the attention on the stimulation of the cells using electrodes. So yeah, the next step will be automation in the pump system, as well as environmental condition.
Yeah, this will help. Yeah, to have this automated. This will be a good step. Yeah, thank you. Okay. Then also I read that COVID might infect or replicate also in eye cells. Can I use the technology also for COVID research?
Yes, you can. You can focus the attention on different tissues. So, of course, COVID takes in consideration the lung epithelium cells, but you can analyze the effect on the lung, as well as the crosstalk between different tissues, in this case, the eye. So you can join together different modules as in a Lego strategy approach, increasing the complexity of your simulation.
Oh, okay, this is nice. Also, I noticed that you have rebranded your logo, Tommaso. The slogan now says closer to humans. I like this very much, but maybe you like to tell us a little bit more about that.
Yes. When we start with our company, we were mainly focused on technology. So we were a technological supplier. Then we increased our service offers, and in particular, the last period, we start also the possibility to develop the biological aspect of the in vitro model. So for us, it's important to say that we are not anymore only a technological supplier, but we are also a partner in the development of these advanced in vitro models. So we want to be closer to the humans also with our service actions.
Yeah, that's right. Yeah, it's an in vitro model, so it's really close. Yeah.
Yeah, you know, it's a multidisciplinary world. So we have the biological experts, and then we also have engineering methods. So we can help from an engineering point of view in order to increase the complexity, but maintaining a very strict correlation with the human reality. So we hope to be helpful in this phase.
Yeah. Okay. Thank you, everybody. If there are any more questions coming up, you may also write us. Just type in and info@pilobiotech.com, or you can also write to Mauser directly. He has written his email address here, so it's t.srana@ivtech.it. And if you have any more questions, just go ahead and dial in. And thank you, everybody, for joining. Please stay tuned in. Yeah, we will have a lot of webinars today. So today is a webinar day. We have had four. One with our partner Vita site. If you know somebody who might be interested in that is about IELTS. And then also, sorry, this is at 5 o'clock. And then at 4 o'clock we have the Emerge, the seventh episode of the Emerge webinar with Reason. So there are a lot of webinars going on today. And also just stay tuned in, have a look at our website at www.pilabiotech.com. And you may watch this recording later, latest next week, on our YouTube channels. And please share this info with your friends and coworkers. And if you have any more questions, just let us know. We are happy to help and see how this will fit your setup. And Tommaso, it's always there to answer questions. And we'll come and see you in Pisa, well, sometime.
Yes, of course, you have to come.
Yeah, we will do. We'll do in summer. I think this would be great. Yeah.
Yes.
To just meet up again in person without a mask. Yeah. I already heard that in Singapore they are allowed now, I think today or yesterday, I don't remember, to not wear a mask outside. Yeah, so big steps also over there in Asia. Yeah, so thank you, everybody. I will stop the recording now, and everybody have a great day. Okay.
Thank you again for your attention. Have a nice day.
Yeah,
Bye-bye.
thank you. Okay. Bye-bye.